I tried the homework.
A whole bunch of stuff happened around with my family. Nothing like really bad, but it just took a lot of time and I got way behind on stuff. And so the grading does take a while because I want to make sure I read it carefully. And sometimes handwriting's not all that good. But I did send out, I uploaded the answers this morning. So you should have an idea, right? You should have a pretty good idea of how you did.
I'm going to go check that then.
Yeah, I put them up. They're handwritten. I didn't do every problem completely to the end. I did a bunch of them, just got it all set up. So you should have an idea of, okay, I'm good. And for some problems, there were methods. I only chose one method. Some problems I did two different methods, got the same answer, and some I didn't. So that'll help you a little bit on there.
By any chance, was number 5 the extra credit?
Yeah, of course it was.
Okay, yeah.
Mariana, I am going to be doing, I've gotten better with the recording, so I'm going to be recording this tonight. It worked in the morning class, so I'll be doing that. I've been having better luck with it lately. Plus, tonight's class will be on the shorter side, so the files aren't as big, so I can get them up into Canvas. Yeah, so number 5, I think you could figure out that was the extra credit, right?
Yeah, I was doing it and I was just like, okay, probably this is the one that I'm going to get wrong, but I just did it out anyway. But I think I might have did it right, but I doubt it.
So
where was it uploaded, the answers?
Up to same place where the homework is. It's just up in files.
Okay.
It says chapter 7, partial solutions.
All right.
It's photographs of my handwriting. They came out sideways for some reason. So Brandon, occasionally in an upper level class, I'll put an extra credit question on a test and not tell anybody it's extra credit. That way everybody tries it.
Yeah.
And so if you made any progress at all, you're going to get some points. And even if it's blank, you're not going to get points off. It was extra.
Are you still in the process of grading the test?
I am.
Okay.
Oh, you just got here, Sean?
Yeah, I'm sorry, I'm a little late.
No, that's all right. I got way behind over the weekend. A bunch of stuff came up with family and I couldn't keep up.
It's okay. Hey, things happen. Like we're all at home now.
Yeah. So I did put the answers up online, so you should be able to get a sense of how you did.
Okay. There was one that I actually kind of like, you're going to see at the end. It's like, I couldn't get it. I just couldn't get, right? I couldn't get like what's that?
Number 5?
Yeah, that was it.
That was extra credit.
Okay. I couldn't get like the algebra to work right. Yeah. And it was coming out with negative number. And I was like, I can't do this.
Yeah, it was an extra credit problem. I didn't say it was extra credit. So
nice.
So that everybody tried it. I know that was mean, but I really don't care. You learned a lot by trying.
Yeah.
I think the last one was like really basic.
Oh, the kite flying?
Yeah.
Mm.
Yeah, you're welcome. That was a gift.
Yeah. I was looking at it, I was like, am I wrong?
Well, I was very skeptical of that first. I looked at it, I was like,
I don't know.
So creating tests is a very creative thing, by the way. You got to come up with a problem that just looks at one thing. And it's possible to put a question on a test that's so easy, it scares everybody. Like you're thinking, it just can't be this easy, right?
Yeah, that was me.
Yeah, so number 8 was pretty straightforward. The fractions all worked out. And it just turned into a U substitution or something like that.
Hey, Professor, I have a question. It's not related to this class, but have you ever solved any of the Putnam questions in like the back of the book?
Yeah, I've tried some of them. I've gotten 1 or 2.
They're nasty. Like some of the harder level ones, I was like, oh my God.
Yeah, people who score high on the Putnam get lots of scholarship offers.
Isn't it like really hard to score high? Like, isn't the average like 2 points or something?
Yeah, something like that. Yeah.
Wow.
Yep. All right. So we're pretty much all here. Mm-hmm. So just to recap, in case you just came in, I'm behind on the grading. The weekend just really got away from me, and I'm behind on all that stuff. I uploaded some of the answers to the test. So if you look at those, you'll at least have a sense of you pretty much did the right thing or something like that. And number 5 was extra credit. Don't worry if it doesn't count against you. If you made any progress at all, you're going to get some points on it. So we'll start out tonight with any homework questions from the by parts homework. And then we're going to start the next section, which is 8.4. Just going to do a couple of examples for tonight, and that's going to be good. And I am now going to start recording. All right, so I'm recording for tonight. So homework questions.
Number 13.
Number 3. Oh, wait, I have to go get the book. Hold on a minute. Here we go. Sorry, Brandon, what did you say, 13?
Yeah.
Oh, okay. So here's number 13. Number 13 is x cubed e to the x dx. So in class, turn this off. It's really dark in here. Whoops. Hold on. So in class last time, we did x to the first e to the x. We did by parts. I think that was the very first one I did. And went straight forward. So in this problem, we have to do by parts 3 times. So it's not quite as bad as it sounds. So because if this was a 5, we do by parts 5 times. If it was a 2, we do by parts twice. So by parts, we do u and dv. And the dx always goes with that. So dv is e to the x, and u is x cubed. Then we do the derivative of u is du. This derivative is 3x squared dx. The integral of dv is v, and the integral of e to the x is e to the x. And then we go into the formula, which is uv minus the integral of v du. So that becomes x cubed e to the x minus the integral of 3x squared e to the x dx. All right. You never touch the uv after you're done. That just stays there. Now we have to do this integral, and I pulled the 3 out because it's a constant. Now we have to do by parts again. So here, u is equal to x squared, dv is equal to e to the x dx, du is 2x dx, and v is e to the x. So we go into the formula again, minus 3. And we do u times v again, which is x squared e to the x, minus v du. I'm going to pull this 2 out. 2 times the integral of x e to the x dx. And now we have one more by part to do. So same thing. It's u is equal to x. dv is equal to e to the x dx. du is dx. And v is e to the x. All right. So our final answer here. Oh, that shouldn't be there. It should be. So that gives us x cubed e to the x minus 3x squared e to the x, and then plus 2 times this. So uv is x e to the x minus the integral of e to the x dx. And so your final answer, without, I ran out of room, it's x cubed e to the x minus 3x squared e to the x plus 2x e to the x minus 2 e to the x plus c. So that's how you do that one. That was yours, right, Brandon?
Yeah.
Yeah, you okay with that one?
Yeah, I'm just like I get a little confused when you do by parts like again.
Yeah, this many times.
Yeah.
Same thing. We did, in class, I did, I think, x times cosine x or x times sine x, one of those. So if it was x squared times cosine, by parts twice. Yep. Now you've seen it. So it's a little frustrating how to do it by parts and you get all done. Oh, I got to do it by parts again. You do that one. Oh, I got to do it by parts again. Yeah. Kind of a cascade thing. What else we got from anything there? Anybody else? All right, well, you can always send me emails with questions and all that kind of stuff. Doesn't have to be right now. So here's what we're doing tonight. Not going to be a very long class tonight. I'm going to give you just one night's worth of information. So we're going to move up to section 8.3, I guess it is. Having a marker that would work would help. All right. Here's what trig integrals look like. Oops, wait a minute, Mariana. Hold on, somebody dropped out and they're coming back in again. Hang on a minute. Make sure she gets in here.
You know, you could turn off the setting where you have to admit people.
Yeah, I know, but I like to have control of that.
Okay.
Mariana, you back okay? I saw you dropped out there. You back in?
Yeah, I'm back.
What, power something or dropped off or cat step on the keyboard, something like that?
I had to switch from my phone to my laptop.
Oh, okay. I know in yesterday's class, my two stat classes yesterday, people were telling me with a storm, some of their morning classes, like all the remote stuff crashed. WebEx crashed, power was going out for people. So here's an integral. Sine x dx. What's the integral of sine of x? What's the integral of sine of x?
Negative cosine.
Yep. So this is just negative cosine x plus a constant. All right. That's a trig integral. The integral of cosine is positive sine. The integral of secant squared is tangent because derivative tangent secant squared. But we're going to look at something like this tonight. So here's an example. We're going to do the integral of sine of x, but not plain old sine of x. We're going to do sine of x cubed times cosine of x dx. So we have sine cubed times cosine. And we're going to do this integral. Method's not bad. There are some general guidelines I can give you, that I'm going to give you at the end of tonight, that work almost all the time. So a lot of times this is going to turn into u substitution. So here's the key. This is just cosine to the first. So this cosine to the first, we're going to let that be our du. We're going to do a u substitution. That's going to be our du. So we're going to let u, we're going to let u equal sine of x. Not sine cubed of x, just sine of x. It has to just be the sine of x. We do the derivative of both sides. We get the derivative of u. We get cosine x dx, which we have right there. So this problem turns into this. This turns into the integral of u cubed du. Sine is u, so this is u cubed. The du has the cosine dx in it. And this gives us 1/4 u to the fourth plus a constant. And that answer is correct. But stylistically and politely, we replace the u by what it was. So we get 1/4 sine to the fourth of x plus a constant. Whoops. And that's the answer to that question. That doesn't seem so bad, right? If it was cosine to the third sine, then the u would be cosine and the du would be negative sine. So pretty straightforward on there. That's because one of these had an exponent of 1. So we're going to look at this more generally. Anybody got a question on this one? All right. So generally for tonight, part 1, we're going to look at integrals like this. No, not like that. We're going to look at them with something darker. That doesn't look so good either. All right. So here's what I have. I have cosine to the exponent m times the sine to the exponent n, even though you can't probably see that very well. So in this general form, the m and the n are non-negative whole numbers. So m and n would be numbers like 0, 1, 2, 3, and so on. Non-negative whole numbers. No fractional exponents, no digital exponents, just non-negative whole numbers, 0, 1, 2, 3, 4, 5. Okay. So here's another example doing this. Let's look at cosine to the third of x times sine to the third x. So we have an exponent of 3 and an exponent of 3. Now I'm just going to change this right now for 4. Okay. It's not going to change anything here. So 4 is an even number and 3 is an odd number. If you have an odd number and subtract 1, what do you get?
An even number?
You do. So I'm going to subtract 1 from the odd number. And write it like that. Now my goal here was to get a trig function with an exponent of 1. So right here, it's going to be a u substitution, and that's going to be our du. Well, if our du is sine, if our derivative is sine, u is going to be the cosine. But we have a problem. We've got an extra sign here. So we have to bring in some trig identities, all that unit circle stuff and all of that kind of thing. From way back in probably pre-calc here. So the unit circle, x squared plus y squared is equal to 1. That's called the unit. Oh, that looks like circle. The word unit refers to the number 1. So $1, 1 hour, 1 minute, 1 millimeter, 1 century. So the radius of our circle is 1. That makes it a unit circle and centered at the axis. From the unit circle, we get the definitions of sine and cosine. So on the unit circle, which trig function is the x associated with? Sine or cosine?
Sine.
Cosine.
X is cosine and y is sine, right? X comes before y in the alphabet, C comes before S. So from here, we get the well-known thing, cosine squared plus sine squared is equal to 1. That's where that identity comes from. They are equivalent expressions. They're both talking about a circle of radius 1 centered at the origin. So all of the trig identities that you know are all based on something being squared. Almost all the trig identities are something being squared. So we're going to do a trig identity on this problem. So we're down to here. So my du has a sign in it. That means my u value is going to be cosine. So derivative of cosine my du, and there's going to be a negative sign in there. So this is going to be u to the fourth. This is going to be du, but we have to get rid of this sine squared. So we do that up here. So sine squared, by a little bit of algebra, you bring the cosine to the other side, and sine squared is equal to 1 minus cosine squared. That's one of the identities. So in this problem, I'm going to take out the sine squared and put that in its place. It's equivalent. So now this integral becomes the integral of cosine to the fourth of x times 1 minus cosine squared x times sine of x dx. So I went from here to here using that identity. I'm just going to stop there for a second. Anybody's got questions? I got to go get some more of my herbal tea here. I'm still struggling with a sore throat. I don't know what's going on. I'll be right back. I have some exotic Asian teas to help with sore throat. Any of the off topic here. Any of you ever been to H Mart up in Edison? Anybody go to H Mart? Highly recommend it. It's a Korean grocery store that's the size of Walmart. And they've got all these interesting exotic fruits and vegetables, and they got rows and rows of all different kinds of teas and stuff like that. It's pretty interesting just to walk around. And it's like a little mini vacation, just getting out of the house for a while. All right, so here we go. Now I'm going to rewrite this. So we have the integral of u to the fourth times 1 minus u squared du. But if u is equal to cosine, then du is equal to negative sine of x dx. So this u substitution, we put this negative out here. So the sine x dx is inside there, and there's our substitutions. And what's the next step now for solving this integral? What do I do next? Now, here's the thing with integration. Every time you do some stuff, you get a brand new integral to look at. So we can just throw all of this out and consider this a brand new problem, right? So now we have a brand new problem.
Why is it negative?
What? This?
Yeah, why is that negative out there?
Because we let u be cosine of x. And when we did the derivative cosine is negative sine of x. That negative is out here. It's a constant. It's -1. So I just pulled it all.
Oh, okay.
Yeah, no, good question. All right. So how do we do this integral? This is like a Calc 1 integral. Just think of this as a brand new problem. What do I do next?
Distribute the u.
Yep, just multiply everything out. So we multiply it out. And then we get u to the fourth minus u to the sixth du. And now we just integrate. So we get negative 1/5 sine to the fifth of x minus 1/7 sine to the seventh x plus c. You can distribute the negative or not, it doesn't matter. So that would be the final answer to that question. And like I suggest, you should do the derivative of your answers. That's where you catch mistakes with constants or something. So to do these derivatives, you need the chain rule on here. So it's a good idea, good practice for reviewing the chain rule. Okay, so what else? Anybody got anything, questions on this? All right. Just going to do a couple of these tonight. This is the whole topic for tonight.
Hey, are you a sin x or cosine x?
Oh, you was cosine. Did I write sine? Oh, I did. I'm sorry. That should be, the final answer should be 1/5 cosine to the 5th minus 1/7 cosine to the 7th of x. Oh, thanks, Jacob. I forgot u is equal to cosine. I was thinking of a different problem. Yeah, that's the final answer there. Thank you. All right.
So I have a question.
Yep.
What if the powers are like greater? Like I guess like, you know, m is 5 and n is like 4 or whatever.
Still, you have an odd number. You have a 5, right? So the numbers don't matter. What matters is if they're odd or even.
Oh, you're trying to get them to look alike, pretty much.
Well, I'm trying to get a single trig function out the back.
Okay.
It's my du. So here's the thing about trig stuff. Once you do a couple of these problems, you'll see there's a general pattern. It doesn't matter what the actual value of the exponents is. We're just looking for an odd one. So even if the numbers were 20 and 17, right? You'd pull one of those off, and then the 17 would be a 16, and you'd just have a single trig function out the back.
Okay, so you're always just trying to isolate one trig.
Yeah.
The power of 1.
So this problem was, what was it? It was, the original problem was cosine to the 4th, and then sine cubed of x, right? That was my original problem?
Right.
All right, so let me show you. So math, real math, is all about looking for patterns and using something called inductive reasoning. Once you see a pattern that a certain kind of problem has the same path to a solution, then the numbers don't matter anymore. So take a wild guess, right? If I were to make this an 11, the solution to the problem really wouldn't change, right? I'd still take one of these and put it out back. And then I'd convert this over. And then I'd have like a 12 and some other number down here. The answer would look very much the same. The pattern. And after my next two examples, I'm going to tell you what that pattern is. Okay. Good question though, Sean.
That 1/5 cosine to the power of 5,
Yeah.
and then minus that looks like a pattern I've seen before, some sort of series.
Oh yeah, there's a lot. Chapter 9 is all about series.
That looks like something I've seen before.
Yeah, it is. So the thing about sines and cosines, it really doesn't matter where you're headed to after this. If you're doing physical engineering, like building machines and roads and stuff, electrical engineering, if you're doing biology, ecology, sines and cosines are everywhere in the real world because everything does this, right? You look at average temperatures in the part of the world we live in, our latitudes. Summer is warm, fall gets cooler, winter is cold, then it starts warming up, cooler and cooler and cooler. So animals in the natural world, predators and preys, those who are food and those who eat, their populations follow each other like this. As the population of the rabbits goes up, the population of foxes goes up because there's a lot of food to eat. Foxes eat all the rabbits, then the rabbit population falls, and then there's not as many foxes. So sines and cosines are everywhere in the real world. Things go round and round. That's why it's so important. So here's another example. Let's pick this one.
So our goal is to have the exponents even of the trig functions in the integral?
Not necessarily. So there's some general guidelines I can give you, but it's not quite like that. So here's another problem. The integral of sine squared x dx, just sine squared. Well, so here the sine has an exponent of 2. What's the exponent on the cosine? There isn't one. What's its exponent?
0.
Yeah, cosine to the 0 is equal to 1, right? So it's this. Well, this isn't, you can't just add 1 to the exponent because this is really sine times sine. So now I'm going to remind you of another kind of identity that you've probably seen, and if you haven't, you're going to see it now. So here we need another trig identity. In some texts, so in the back cover of your book, I think it's the back cover. Nope, front cover. Pretty much all calc books, even if it's not this one. So up here in the front cover on the back page, I know you can't read it, are all the trig identities, the unit circle, radians to degrees, degrees to radians, and all that kind of stuff. So they're all up in the front cover of the book. So the book is going to call this the half angle formula, but I'm going to call this power reducing. So we have cosine squared, and we have sine squared. The problem in our integral is that exponent of 2. This is going to reduce this exponent. It's going to reduce that power down. So these formulas look identical. They both have a 2 in the bottom. They both have a 2. Over here, we get the cosine of 2x. And down here, we get the cosine of 2x. The only difference is what's in between. One of these has a plus sign, one of these has a negative sign. For those of you who vaguely remember these, if you do, which one is which? Formulas are identical except for the positive or negative signs here. Anybody know?
The cosine squared is positive and the sine squared is negative.
How positive are you that it's positive?
About maybe 87%.
Pretty good. So Brandon is right. Here's how I always remember it. Think of sine as sinus, and this is minus, and the other one is plus. So those are, you don't have to memorize them anyhow, but you will after a while. So both of these will turn a sine and a cosine to the second power into a cosine to the first power with that little catch of 2 in there. So that's what we're going to use to do the problem I have on this other whiteboard.
How is this derived?
How is that derived? Do you still have your pre-calc book?
No, but I guess I can find it.
Well, you can find it or you can Google it on something. I don't want to take a bunch of time to go over that in here.
I got it. I was asking if it might be simple or whatever. Okay.
Yeah, it uses some other identities to get there, and it's not that it's really all that difficult, but 15 minutes or something like that. Okay. So we're going to use power reducing on here. So this integral becomes the integral of 1 minus cosine of 2x dx. I don't need parentheses here. This fraction bar counts as a grouping symbol, so I don't need parentheses. Okay, so now this 2 is just a constant, so we might as well just pull that right out. Now I need parentheses. And now we can do the integral. So this power reducing comes up quite a bit. So the 1/2 is a constant. The integral of 1 with respect to x is just x. And now we have to do the integral of negative cosine 2x. Well, the integral of negative cosine is negative sine, so we're going to have that, but we have to deal with this 2. How do we deal with this 2? Anybody know? Starts with a u, which is pretty much how we do it. So we're going to do a little u substitution here. U is going to equal to x. That means du is equal to 2 dx. So 1/2 du is equal to dx. So we get minus the integral with the 1/2 in the front, cosine of u du. So that's going to come up a little bit. It's done the same way every time. And now we can finish off the problem. So we get 1/2 x minus 1/2, and the integral of cosine is sine. Here's the negative. So we get sine of u, or just 2x, and then plus c. So that's the integral of the sine of sine squared x dx. You can multiply through by the 1/2 or not. At this point, you know, that's not really kind of what we're doing tonight. So cosine squared plus sine squared equals 1. All the identities come from that, and the power reducing one. Those will come up a bunch in the homeworks from now on. A question on this one at all? All right, do one more example, and that's going to be it for tonight. And I'm using t's because I got tired of x's. We're all tired of x's, I just imagine. Okay, now, that looks pretty awful. So a lot of times, there's like folklore in math a lot. One of the folklores is, in the calculus class, if a problem looks really, really ugly, often it turns out to be not so bad. If a problem looks really, really simple, you might be there for 3 pages of work here. So there's going to be a u substitution, but first we have this odd number. I'm going to get rid of that. So I'm going to rewrite this. I have a cosine to the first out there. That's going to be du. It's going to be a u substitution. U substitution happens a lot in this section. So that means my u is going to be sine, and du is going to be cosine of t dt, and that's all right there. So now my integral becomes this. On the bottom, I have the square root of u. On the back, we have du. And this cosine squared, I'm going to change that to 1 minus sine squared. So I'm going to change this cosine squared into 1 minus sine squared, which gives me 1 minus u squared on the top. So now the problem looks a little bit better. A lot better, maybe. A little better. So what we have here is 1 minus u squared over u to the 1/2 power du. So we've gone from here to here by a u substitution. Now, think of this as a brand new problem. How do we solve this equation? Just think of this as a brand new problem. What's the method?
Separate the terms.
Yep. So I'm going to just separate it in. Good, Michaela. Very nice. So we're going to get 1 over u to the 1/2 minus u squared over u to the 1/2 u. I just split it terms on the top. Then I'm going to simplify. 1 over u to the 1/2 is just u to the negative 1/2. U squared, I can think of u squared as u to the 4/2 over u to the 1/2. So 4/2 minus 1/2, this gives me u to the 3/2 du. So just a little bit of exponent algebra there. And now we can integrate. Add 1 to the exponent. Negative 1/2 plus 1 is u to the positive 1/2. Divide by the new exponent. 3/2 plus 1 is 5/2. Divide by the new exponent. Plus k, plus a constant. That is a correct answer. That answer is correct, but if you're working engineering or something, there's a good chance you'll be doing consulting, meaning other companies are going to come and hire your company to help them with problems. If they give you a problem in terms of X, you should give it back. So this becomes 2 times sine to the 1/2 of t minus 2/5 sine to the 5/2 power of t plus a constant. And that would be the answer. Both of these are acceptable and equivalent, but that's what you see in the back of the book. So Sean, there's like some more series stuff going on in here. So
I had a question about integration by parts. I'm sorry to go back to that.
Well, that's all right. Let me just see if anybody has any questions on this. So when you do a couple of these homework problems, you'll start to sort of pick up a pattern. Just like by parts, you'll pick up a pattern as well. So let me just wrap this up a minute, Sean, and then I'll go to your by parts question.
Okay.
All right. So in general, so just sort of a general idea for how to start these. It's not a rule that's necessarily going to work every time, but it's a good starting point. All right. If at least one, so Brandon and Nicole is starting to sound like discrete math, right? If at least one of mn is odd, then pull one off and use u substitution.
Are you always going to use u substitution on the one that you like pull off?
Well, the whole problem is a u substitution. You're not doing u substitution to one or the other. The whole problem becomes. So at least one or both. So let's say if n was an odd number, like 5, pull one off, put sine to the first out in the back, that will leave you with sine to the fourth, which you could convert into cosines using the identity. If both of them are odd, then just pick one. Pick the lower number and just go ahead and do this, all right? So if one of your exponents is odd, generally it's going to be a u substitution problem. If at least one of those is not odd, that means they're both. If M and N are both even, then use power reducing. If they're both even, this won't work. You can't just have a single one out in the back. So if they're both even, like a 2 and a 4 or a 2 and a 2, you're going to end up with power reducing formulas. So this is just a guideline. It might not work for every problem. Like that last problem had a square root of sine in the denominator, but that sine had a power of 1 on it. So that's how that worked. And the cosine was cosine cubed. So we pulled 1 off on there. So this is sort of a general guideline that's going to work. On Thursday, we're going to do tangents and secants because they're connected in calculus also. So,
yeah. Quick question. So if it's in a square root, that's considered odd?
No, that was sort of a problem that didn't fit into this at all. The key to that last problem was the square root had a sine to the first, so there was cosine cubed on the top. So I pulled one of the cosines off. So that was a problem that didn't quite fit this. Most of the problems are going to be looking like this.
Okay. If I had something, let's say a cosine squared t over a root sine t, would I use the power reducing or?
Let's see what you had there. So you had, so what on the top?
Let's say cosine squared t.
Okay.
And on bottom you have a root sine t.
Ah, cosine squared. Yeah, that'd be a really hard problem, by the way. You're not going to see those. In fact.
Oh, okay, because I just didn't know what to use in that situation. I don't know if a root is considered odd or even.
Is that a problem from the book?
Oh, no. I was just thinking in my head.
Oh, yeah. So that problem, there's a good chance that problem can't be done. That problem might have to be done by something called numerical analysis, which means you actually use actual rectangles, right? And you have a computer do an estimation on it. A lot of integrals in the real world can't be done at all. You can't actually write them in what's closed form. You have to use computer simulations to estimate the answer. The problems in the textbook are all designed so that they do have answers on there. That was a good question, though. So, yeah, that problem I don't think that problem can be done. Good question, though. All right. So not a whole lot of homework tonight. It's just going to look like that. Thursday, we do tangents and secants. Secants can be a bit of a problem, but we'll get through it, okay? So that's it for tonight. I recorded this. I'll get that up later, and I am working on your test, and I apologize it's taking so long. I'm probably going to just add a few points to everybody's test grade because I've caused all this anxiety by not getting them done fast. And again, number 5 was extra credit. If you even left it blank, not even going to affect your grade. If you attempted some stuff and made any progress at all, you're going to get some points for that, all right? Okie dokie, that's it. I'm going to stop the recording now. And Sean, if you want to hang out for a few minutes, or ask your question, that goes by parts so everybody can hang out. So Sean, what was your by parts question?
So I'm trying to figure out how to word this, but I understand the rules, like the actual the rules, but I guess why are we minusing by the integral of v du? Like why?
Because
do that?
Well, that's where the formula came from. So by parts comes from the product rule when you do a derivative. By parts